Alright, hello everybody. This is Dr. Paddington again, and in this video I'd like to talk to you all about something called classifying bond types. And when I talk about bond types, we've talked a lot about how chemicals react with each other. One thing we haven't really talked about to any great length is the different sorts of bonds that exist between atoms. Back earlier on in the semester we did differentiate between ionic and covalent or molecular compounds, but we didn't really specify much about those other than mentioning in ionic compounds electrons were transferred between elements, and in covalent compounds electrons were shared. And we'd also said that in ionic electrons were transferred because we had a metal and a non-metal, and in a covalent compound, a molecular compound, we had two non-metals, but we didn't really talk about exactly why that was the case. And that's one of the things that we're going to focus on, because we're going to see a little bit about the difference between ionic bonds, covalent bonds, and the fact there's more than one different type of covalent bond. A normal covalent bond, and there's something called a polar covalent bond. So, the best way to start off here would be to talk about a molecule like hydrogen, for example. Here's a molecule of hydrogen with the bond shown connecting the two hydrogen atoms together. Now, I'm not going to get into the specifics of exactly why the bond forms. What I do want you guys to understand, though, if we had to draw a location of where the electrons would be in that bond, we know there's two of them. There's two electrons, one from each hydrogen. Because these atoms are the same, the electrons are essentially shared, or we show them being shared right in the middle of the bond. So intermediate between one hydrogen and the other hydrogen. And that's simply because those two hydrogens are exactly the same. Neither one is pulling the electrons more than the other one, so the electrons sit right in the middle. And that's always the case for when you have a molecule of two of the same element bound together, like chlorine, for example, fluorine, for example. But this is an important thing for us to understand in terms of the start of classifying bond types. The electrons are right in the middle. And notice the electrons are shared, they're not transferred. In each case we have two non-metals, so we would expect electrons to be shared. And these are called covalent bonds. They're not a special type of covalent bond because the electrons are right in the middle. Things do start to be different, though, when we have different elements that are bound together. For example, if we were to take hydrogen and chlorine, anybody can tell you that hydrogen and chlorine are not the same. And so when we make a molecule of HCl here, it's not quite the same in terms of where the electrons are. This hydrogen still donates one, this chlorine donates one, and the two electrons are shared. But in this case, they're not shared directly in the middle. They're shared, displaced towards a particular element. In this case, they are displaced towards chlorine. If we were to draw out a molecule of HF, then we would see exactly the same thing, except the electrons will be displaced even further towards fluorine. And if we were to do something like HBr, for example, it's still exactly the same sort of thing, but for some reason the electrons would be closer to the middle than for HF or HCl. So it might look something like this, for example. So for some reason the electrons in this bond are displaced further towards fluorine, than they are for chlorine or bromine. Now, why is that? Well, the reason is actually this one word right here. This word called electronegativity. This is an important word. Electronegativity, it's a measure of how strongly an atom pulls electrons towards itself. Fluorine is the most electronegative element in the whole table. In fact, electronegativity increases left to right and bottom to top in the periodic table, so that's the most electronegative element. So what that means is fluorine pulls electrons towards itself stronger than anything else. That's why the electrons in HF are displaced towards fluorine. If fluorine is the most electronegative element, then you would expect us to be able to say, well, then chlorine's not quite as electronegative and bromine's less electronegative still, and that's exactly what the case is. Now, it turns out that you can quantify this electronegativity difference because textbooks, and our textbook included, has a table of electronegativity values for every single element known. And so you can actually calculate the electronegativity difference between the two elements involved and actually figure out the type of bond that you have. Okay, and okay, I'm being joined by a guest speaker, my cat, right now. So if you hear some purring or meowing, it's not me. I don't usually meow unless I'm drunk, or I don't know. Yes, thank you, Emma. Okay, so we were talking about electronegativity difference, and we talked about how we could quantify this. And basically there are three things that we want to look at, or three possible outcomes we can have for our electronegativity difference. We can have a small difference. And if we have a small difference, as is the case for these three, where the difference here is 0, right? Small difference gives us something called just a standard covalent bond. Now, and one example of that would be, for example, like we just said, Cl2. An intermediate electronegativity difference is between 0.4 and 2.0, so obviously a larger difference than here. That gives us a bond type known as polar covalent. And polar covalent would be an example of this, this, and this. So HCl would be an example of that. And then a particularly large electronegativity difference would be where you have a situation where the electronegativity difference is so big, this atom pulls the electrons towards itself so much more than this that it actually pulls them and breaks the bond. So you go from an ionic bond, so you go from a covalent bond where the electrons are shared to an ionic bond where the electrons are actually transferred. And they're always transferred from the metal to the non-metal. So for example, sodium chloride is Na+, and Cl-. We've seen this before. And that sort of bond, where those electrons are actually transferred, is known as ionic. And like I said, you can use the electronegativity table in your textbook to see or to calculate, to quantify the difference between the electronegativities of your atoms in general. Okay, I'm trying to turn over the page. Can you piss off for a minute? Thank you. So the electronegativity difference here for chlorine, delta En here. Chlorine has an electronegativity value of 3.0, and of course 3.0 minus 3.0 gives a difference of 0. Therefore that fits a covalent bond. HCl. Now chlorine, as we said, the electronegativity is 3.0. And I'm not going to assume you know these numbers. What I'm going to assume is that you can do is use a table of these numbers to calculate them if you need to. Hydrogen is 2.1, gives us a difference of 0.9, which fits right in the intermediate range. Now for sodium and chlorine, chlorine again is 3.0. Notice we're always taking the largest value first and subtracting the smallest value from it. Sodium has an electronegativity of 0.9. giving us a difference of 2.1. So these three all fit the ranges that we would expect here. So that's a little bit of an overview of the different types of bonds that we can have. Now what I want to go through is a couple of examples to illustrate this. All right. So a question would be, for example, determine whether the bond between the following elements is covalent, and this is sometimes known as pure covalent, but we're just going to usually stick with covalent. Polar covalent or ionic. So which one of those three is it? And we need an electronegativity table for this. So if we say the first one we have is iodine and iodine, well, this one's actually pretty easy because you've got two atoms of the same element. If it's two atoms of the same element, the electronegativity difference is by definition going to be 0. Therefore, that's just covalent. The electrons are shared equally between each iodine. And Emma is using my pen as a rubbing post now. So if I start writing like I'm on drugs or something, then I'm not really on drugs. Well, not tonight anyway. Hey, get off, you little shit. Oh, sorry, I didn't say shit. Oh, okay, I did. Next ones would be cesium and bromine. Again, if you have an electronegativity table, which we do, cesium has an electronegativity of bromine is 2.8, cesium is 0.7, giving a difference of 0.1. Ionic, as you would expect, because cesium's a metal, bromine's a non-metal. Phosphorus and oxygen. Now both of these are non-metals, so the first thing you can say is, well, it's going to be covalent of some sort, but is it covalent or polar covalent? Well, we'll see. Oxygen has an electronegativity of 3.5. Phosphorus has electronegativity of 2.1, giving a difference of 1.4. Therefore, polar covalent. All right. So what's the difference between covalent and polar covalent? Imagine, if you will, the bond between hydrogen atoms that we saw before. Neutral, not very special, not particularly interesting, blah, blah, blah. If we look at HCl, the electrons, as we saw before, are spaced or oriented closer to chlorine. Because of that, because the electrons are closer to chlorine and electrons have a negative charge, they're closer to the chlorine for more time than they are to the hydrogen. And that builds up a small negative charge on the side of the chlorine and a small positive charge on the side of the hydrogen. This is a charge separation known as a dipole. The larger the electronegativity difference, the larger the dipole. All right. So if we were to look at, say, HF, we know fluorine's more electronegative than chlorine. In fact, I said before, fluorine is the most electronegative element in the whole table. There's still a delta minus and delta plus here, but the dipole for HF is larger than for HCl. Because of the electronegativity of fluorine. All right. Now this dipole, this charge separation here, is going to have some importance. It's going to have particular importance when we talk about Lewis structures later on, because we can talk about polarity of bonds, and polarity of bonds leads directly into polarity of molecules. And being able to recognize if a molecule is polar or not is going a long way to understanding its properties. Okay, for example, there is a reason why ethanol dissolves in water and oil doesn't dissolve in water. All right, and it's all to do with the structures and how they complement each other. All right, let's just do a couple more and then we'll end. HNO, silicon and chlorine. magnesium, and fluorine. Alright, so it's not a bad idea to get out your textbook, find the electronegativity table. It's kind of a interesting looking thing. It's presented in 3 dimensions with the well, you'll see it. The electronegativity of oxygen is higher than hydrogen. So it's 3.5 for oxygen minus 2.1 for hydrogen, giving a difference of 1.4. And if you remember which one that classifies it as polar covalent. Silicon and chlorine. Silicon's a metalloid, not a metal. So this probably won't be ionic, but we'll see. Silicon is chlorine's 3.0, silicon is 1.8. Difference there of 1.2. So also polar covalent. Magnesium and fluorine. Magnesium's a metal, fluorine's a non-metal. We know fluorine's the most electronegative element in the table. This is more than likely, well, this is actually almost a guarantee of this being ionic because we have a metal and a non-metal, but let's check for sure. Fluorine has an electronegativity of 4.0. Magnesium is 1.2. The difference there is actually pretty big, 2.8, so it's ionic. Alright, and that is how we can use how we can classify bond types using electronegativity. Thank you.